alaikum. Today we have head loss in pipes and fittings. So why I measure head loss in pipes and fittings? That's because it's very important if you design piping system, if you design fluid system and you want to put a pump, so it's very important to measure how much the pipes or fittings can create friction and head loss, so you can choose your pump based on this amount of head loss. So it should be calculated and included in the system curve. So it's very important to use. So now today is head loss and pipes and fittings. So let's start with some principles, fluid mechanics principles. Already, I'm sure you already know it, but let's make like a quick revise. So for any given mass, it has different energies. Potential energy, and it's called potential because it's potential to make work. So if you have a mass, and this mass you lift it above the surface, and then you remove your hand, so it will fall. So this is work. So as you put your hands up, then you have more potential energy, and potential because once it's future energy. So once you remove your hand, it will fall down and it will create work in future, provided that you remove your hand. So this is called potential energy, and it's equal the mass times g, accelerating gravity, times the height. Okay, so and also if this object is moving, so it acquires another energy is called kinetic energy or kinetic energy, and it's equal to half times mass times squared velocity. If this object is fluid, so it has more energy, and it's called hydraulic energy, and hydraulic energy is specific for fluid. So it's energy due to the pressure of the fluid and due to the volume of the fluid. So it will be P times V, pressure times volume. So this is the energy it's used to design the dams, and it's used to design the machines to create energy. So this is hydraulic energy. So suppose we have this energy, the accumulation or the summation of this energy is mgz plus half mv squared plus pv. So this is the energies that found in fluid. Okay, now this fluid is continuous. So, and I can separate each one. So let's divide them by constant. So this constant may be mass or volume. Okay, so but we prefer to divide them per mass, not volume. Why? Because mass is conservative quantity, doesn't affect by temperature. Volume, it's affected by temperature. If the temperature increase or decrease, so the volume change as well. So, but mass is conservative. So it's better to divide this equation by mass. So then PV by mass, so it will be, this is the 1 over rho. So it will be P over rho plus the kinetic energy, so it will be half, so it will be V squared over 2 plus GZ. So, and this part is constant. Okay, this is in terms of energy. If I divide the energy per gravity, acceleration gravity, g, the units will be z, or in terms of meter. So, and it's called head. So it's most applicable in calculations, easy to calculate in calculation, especially if you want to design a pump, if you want to create a system curve, to put a pump in the system curve. So it's better to convert it in terms of energy to head. So this is called head. P over rho g, so just I divided by g, add g here. So P by rho g plus V squared by 2g plus z, g minus, divided g, so it will be cancelled to g. So now, as you know, mass is conservative quantity, momentum is conservative quantity, and energy also is conservative quantity. So that means the energy acquired by one mass should be equal to energy acquired by one mass as well. So if I have a pipe and this pipe, so if I take 1 kilogram of pipe, that means this 1 kilogram have total energy equal to this 1 kilogram if I pass here. Should be. Okay? And I'll tell you why I said should be. Now, if I have like the same pipe but some enlargement, so part of the pipe is larger than the other pipe. So the same, 1 kilogram here will be equal, total energy in 1 kilogram will be equal to 1 kilogram. See, here we have a different, because this one's smaller and this is larger, so the cross section is different here. So the total energy here is equal to total energy here. But now you can see here the area here is less. Okay, so the area that fluid push or stress has a stress on the wall is less than this. That means the pressure here, the pressure at this point is higher. Okay, but so this pressure is higher, but here we have the you can say here, since the diameter here is higher, then that means the velocity is small. You know, AV equal AV. Okay, since the mass is conservative, that means rho times Q1 equal rho times Q2. That means if rho is constant for the same fluid, so rho will cancel out. So A1 Q is A1 V1, A2 V2. So that means A1 V1 equal A2 V2. So when the area increases, the velocity will decrease. So here when we have a larger area, then smaller velocity. So the velocity will compensate for pressure. Okay. Okay. So now also here, if we have like different in Z, okay. So this one potential energy is different than this one. Okay. So this has a lower and this is a higher. Okay. But here also we have, it will affect on the P. So for the higher it will be less. Okay. And here we have a higher. Okay, pressure. So now, so whatever you change in some parameters of energy, the total should be constant. So then we can apply to Bernoulli equation. Bernoulli equation says P1 over rho g plus V1 over 2g plus Z1. So this is the first part equals the second part because it's conservative. P2 over rho g plus V squared over 2g plus Z2. I said it should be because actually it's not actual. It's not very conservative because we have some dissipation of energy. What we do by what we mean by dissipation, when energy, kinetic energy, when it moves from the first point to second point, okay, there's some kinetic energy converts to heat. Okay, converts to heat. So it's in terms of mechanical fluid mechanics, it's dissipation, or it's not equal, but actually it's still equal because it's energy. Heat still energy, but it's useless energy. I can't utilize this heat. So for me, it's energy loss, or it's we can say it's loss energy. So due to the friction when fluid flow from first point to second point, and due to the friction with the wall of the pipe, so it will be friction. So now EF, we can say this is EF, is proportional to kinetic energy. So as the kinetic energy increases, we have more friction, but in the opposite way. So it's also energy, but in opposite way. So EF, this is the energy due to friction, proportional to kinetic energy, V squared over 2g. And in terms of head, HL, also head loss, proportional to V squared over 2g. So we can replace the proportional constant to KF. So HL is equal Kf V squared over 2G. And Kf is called loss coefficient. Loss coefficient. So Kf is loss coefficient and it's compensate for any loss. This means friction. Also, if you have a change in momentum, like fluid change should have a specific momentum, then you force the fluid to go right or to go left. So there's change in momentum. Okay. So this is also loss. Also, if there is eddies in the eddies, so this, you can find it in the surface when the directions also when the direction change. So all this found in Kf. So it's Kf compensates for all this loss of energy. If and it can be used for applied for pipe or fittings or valves. So the same law applies for all. HL equal Kf V squared over 2G. For pipe system, it's easy to determine the Kf because it's factor of three things: diameter of the pipe, and length of the pipe, and the friction factor. So if you know the diameter and you know the height, the length of the pipe, and you know the friction factor, so you can determine the loss coefficient. It be more complicated for other fittings because the configuration is different. For example, if you have like curve like this, fitting like this, so it's difficult. It's not linear. It's not easy to find it. So it has more complicated equation. Okay, but for pipe, circular pipe, it's equal for FL over D. F is called fanning friction factor. If you use another factor called Darcy friction factor, then no need for 4. It's only F times L over D. So it's based. If you are using fanning friction factor, so Kf equal 4 FL over D. If you are using a Darcy friction factor, so it will be FL over D. And fanning friction factor is mostly used by chemical engineers, while Darcy friction factor is mostly used by civil and mechanical engineers. So if your textbook is mainly for mechanical and for civil, they probably use Darcy and Darcy FL over D. But if you are using chemical engineer textbook, you probably find it fanning friction factor and found Kf equal 4 FL over D. So since HL head loss, it's head loss, so I can add it to the energy balance equation and add it here in terms of HL because it's loss. Okay, so P1 over rho G plus V1 squared over 2G plus Z1 minus HL, okay, equal P2 rho G plus V squared 2 over 2G plus Z2. Okay, so this is my equation. Now I want to determine the objective of today's experiment is to find HL. Okay, for pipe or for fitting. So let's start with pipe. So now we have this pipe. Okay, let's apply Bernoulli equation. P1 minus P2. Okay, if I had rearranged this equation, so I can HL on the term, right hand term, okay, equal P1 minus P2 over rho G plus V1 squared minus V2 squared over 2G plus Z1 minus Z2. So now, since 2 points are on the same level, that means Z1 equal Z2, so Z1 minus Z2 will be 0. Also, there is no difference in the diameter, and as we said, A1 V1 equal A2 V2. So if A1 equal A2, then V1 should be equal V2. So then, since V2 equal V1, so this term also equals 0. then P1 minus P2 over rho G will equal HL. So P1 minus P2 over rho G equals HL. So if I want to determine HL, just measure the pressure drop between 2 points, P1 and P2. So now to measure the pressure drop, I can connect a manometer between 2 points. So just connect 2 manometer, okay, like this point. Okay. So the pressure drop P1 minus P2 is the readings of this manometer, delta H, delta rho G. Delta H is the difference in the heights of the manometer. This is delta H. Delta rho is the difference between two fluids. So I have fluid 1 and fluid 2. So if this fluid is water and this fluid is air, then air, the density of air, delta rho, air is 1, is negligible, almost negligible. So I only will consider the density of water. So it will be delta H rho G. And the same if I use mercury instead of water against air. So it will be delta H rho for mercury G. But sometimes you are using two fluids, two different fluids. That means you have mercury and water. So if you are using mercury and water, so both are significant density. So delta, you can't ignore any of them. So it will be delta rho will be the density of mercury minus the density of fluid, water, times G. So now you calculate the pressure drop in 2 points, then apply here that data taken from the manometer divided by rho G, so it will be equal HL. Of course, if you are using only water manometer, then you have delta H rho G, and you have here delta rho G, so rho G will cancel with rho G. But this is only when the manometer is water and air. But if you are using mercury, you can't use. If you are use mercury water, you can't use as well. Okay. So this how to find the HL. How to find HL experimentally. So you can change the flow rate. Every time you change the flow rate, you have more head loss. So you can plot HL, okay, against V squared over 2G. So we said HL equal KF V squared over 2G. We already said this. So if you plot HL against V squared over 2G, the kinetic head, then the slope will be the loss coefficient. And as we said again, for the pipe, KF equal 4FL over D, where F is the fanning friction factor. So you can calculate the fanning friction factor experimentally. Now we can also find the friction factor empirically using Moody chart or other empirical equation. So you will find a lot of empirical equation you can use. But for all of them, you have to make sure that this equation is for Darcy or for fanning friction factor. Now we'll use Moody chart. Moody chart is also empirical graph to find fanning friction factor or Darcy friction factor. The difference between Darcy and fanning will be in the laminar part. We have 3 reasons: laminar flow, transient flow, and fully developed turbulent flow. So the difference between Moody, the fanning friction factor, and Darcy friction factor in the laminar flow. In laminar flow, F equal 16 over Reynolds number, linear. This is for fanning. While in Darcy Moody chart, you will find F equal 64 over Reynolds. This is for Darcy. As we said, Darcy is 4 times fanning. That's why it's equal 64. So Moody chart, if you calculate your Reynolds number, you know Reynolds number equal Reynolds D, the diameter, velocity, density, and viscosity. So if your Reynolds number about less 2000 or less, okay, so it will be laminar. If it's above 4,000, it will be turbulent. If it's in between, it will be transient. So now Moody chart is divided into 3 sections: laminar, transient, and fully turbulent. Of course, we have something called critical, but critical, this part is critical, so it's nothing. There's no correlation for it. Okay. For laminar flow, the friction factor based on only Reynolds number. So we have Reynolds number, we have friction factor, so it's only based on Reynolds number. So F equal 16 over Reynolds number. For transit, because it's laminar flow, okay? So in transient, okay, in fully turbulent, I will start with fully turbulent. In fully turbulent, the friction factor there is no, we can say no relation between Reynolds number and friction factor. So it only depends on the relative roughness. So we have relative roughness. Relative roughness is, we can take this part to draw relative roughness. So if you have like roughness in the pipe, this is the internal part of pipe. And this one, the dimension of this one is epsilon. So epsilon over D is called relative roughness. So how much your pipe is rough from inside. So this is the relative roughness. So when the fluid is fully developed, okay, so it only depends on relative roughness, okay, relative roughness. So as the relative roughness increase, also the friction increase. So it's straight line because it has no contribution from the Reynolds number to the friction factor. For the transient, it pulls effect. Relative roughness, this is over D. Okay, so both will affect Reynolds number and the relative roughness. So you will find the curve is like quadrupolar like this. Polynomial like this. So you have 3 sections. Laminar, it's independent on relative roughness, only depends on the Reynolds number. For the fully turbulent, independent of Reynolds number, only based on relative roughness. And here we have transit based on both. Okay, so you can find your empirical friction factor, finding friction factor or Darcy friction factor using Moody chart. Now we finished the part for pipe. Let's go for fittings. What is fitting? It's any type that's used to connect 2 pipes. For example, if you have a pipe, okay, and you want to change the direction of fluid, so you can put fitting between them. Okay. Also, if you want to change the amount, if you want to put, you have a larger pipe and smaller pipe, and you want to connect both together, so you use this connection. Fittings is called also minor head loss. So for the head loss in pipe is called major head loss, and here is called minor head loss because its contribution to head loss is smaller than the pipe, but it's still significant. So you have to calculate to find it. So the same rule, okay. We can HL equal KF V squared over 2G, as we said. It's applied for all, for pipes, for fittings, for valve. So HL, but we can't easily find the KF like pipe. We said in pipe it's equal 4F L over D. Okay, so we can find it, but it's more complicated and it has a longer empirical equations. You can find their empirical equation, but you will find it more complicated. So it's easy to find it by experiment. So we have different ways. Most of them are tabulated. So for each pipe, KF, and you can find it in textbook for different times. And why it's tabulated? Because they are considered constant. So why is it considered constant? As you remember here, we said for friction factor at higher fully turbulent, it will be only depends on the relative roughness and has no contribution. Real number has no contribution. So only based on the relative roughness. So since in the most application of fittings in industry and most of industry are used in fully turbulent fluid, so GR has a constant Kf because most of the application are for fully turbulent, fully developed fluid. Okay, so we have two types of fitting. We have fittings that has fittings of same diameter. So same diameter, so we'll apply the same rule like we applied in head. So delta P over rho G, okay, delta P over rho G equal HL, and HL equal Kf V squared over 2G. So you can, by plotting delta P over rho G against V squared over 2G, you can find Kf directly from the slope, like similar like we did here. If you have fittings that have different diameter, that means enlargement or contraction. Enlargement, so you have a smaller pipe connected to larger pipe. Or contraction, it's also known as expansion. Or contraction, so larger pipe connected to smaller pipe. Here we can't apply the regular Bernoulli equation by cancel the V squared and cancel the Z. We already can cancel the Z because both of them on the same level, but we can't cancel V2 minus V1 squared over 2G because the V, the kinetic head, it changed. There's contribution from the kinetic head. So the equation will be different. We can't say here delta P over rho G equal HL. No, we can't use because here we have also contribution from the kinetic head. So in case of enlargement, let's apply Bernoulli equation P1 over rho G V1 squared over 2G plus Z1 minus HL equal P2 over rho G plus V squared 2 over 2G plus Z2. So now HL equal both P1 minus P2 over rho G plus the head, difference in head. Okay, to simplify this equation, as we know, A1 V1 equal A2 V2. So we have two speeds. First speed is higher than the second speed. So let's cancel the second one. So V2 equal A1 over A2 times V1 by, as you know, by D squared. So we can by and by will cancel out. So and 4 will cancel out. So we have D1 squared over D2 squared. So smaller diameter over larger diameter times V. So smaller D small over D capital, okay, or smaller over larger equal beta. So we can say V2 equal beta squared times V1. So V2 squared equal P4 squared, beta powered 4 times V1 squared. Now let's apply. Let's do the substitution to this equation. So HL equal P1 minus P2 over rho G plus V1 squared minus P4 times P powered 4 times V1 squared over 2G. So we can take this one as a common factor. So HL equal P1 minus P2 over rho G plus V1 squared over 2G, 1 minus beta powered 4. So now we can again plot, when you calculate the HL, when you calculate for different speed, which speed you should choose? We use the higher speed. Higher speed here is the first point. So HL, V squared over 2G, we can calculate KF and then KF equal, we can find directly KF, okay? So we found HL, okay? And then found V squared over 2G, so can we found KF. The opposite way for contraction. So we can find, if we apply the same Bernoulli equation, you will get the opposite equation. HL equal P1 minus P2 over rho G. Instead of plus, we have here V squared 2 over 2g. So here it was V1, here it was V2. So it's also the higher speed. Okay, 1 minus beta powered 4. Okay, so we'll do the same steps we did here. Last thing we have is for variable K fitting. Some fittings has different or variable K, like valve. So when you close the valve, the K increase. As you close it, the K increase. So now we can do our experiment also. We can find K as 25%, 55%, 75%. You can open the valve totally and then close it totally and find how many turns. Okay, suppose that it's totally opened and when you close it, the round was 4 rounds. Then for 50, each one round represents 25%. So 2 rounds, 50%, 3, and so on. Then you can also, for each round or for certain close value, you can find the Kf for the fitting. So that's all the theory and explanation on the experiment. Now we can start our experiment now. This experiment can be used to determine the head loss for pipe, fittings, and valve. So here, this system has a different pipe. We have 1, 2, 3, 4 pipes. All of them has the same length, but the difference here in the diameter. So we have 6.5 smooth pipe, then 9 smooth pipe. So both are smooth, but the different in diameter. Also, we have here rough pump. So it's 14 here, 14 rough pump. This rough from inside, artificial rough, and this is smooth. Okay. So if we want to test the effect of roughness, we can compare between this one and this one. If you want to change the effect of diameter, you can this one and this one. Okay. So this is for pipe. For fittings, we have different fittings. We have here, we have elbow fittings. We have also 90% bend. We have also contraction. This is enlargement, and on the other part we have contraction and contraction. So the purpose here, we want to measure the Kf. So we have 2 points. This is point 1 and point 2. If you want to measure the enlargement, if you want enlarge as well. If you want to measure fittings, for example, 45 elbow, this is the 2 points, first point and second point. If you want to measure the pressure drop in pipe, so this is the pipe I want to measure. So this is the first point and this is the second point. Or let's see, yes, this is the first point and second point because we have the flow like this. Okay. Now, the most important here is to have the system free of air bubbles because air bubbles in the system will affect on the reading of the manometer. Here we have 2 types of manometer. This is water air manometer. So water air manometer. So the pressure drop here, when you calculate the pressure drop, it will be delta H, the difference of H here, times rho. It will be the rho of water only because air is negligible, times g, acceleration gravity. For the other part of manometer, we have mercury and water. So the pressure drop here will be delta H, the difference of the height between the 2 arms, times delta rho. Since we have mercury and water and both are significant, so we have calculated the difference between them, G. Okay, so now what we will do, we'll open the system. Okay, open the flow rate. And now we want, the first step is to exclude all air from the system. So the system has already air bubbles inside. So to remove all air bubbles, okay, we first step, so as you see, there's a lot of air in the system. I'm trying to take all the air out. Okay. Now the water is flowing continuously without bubbling, so I can close it. Okay. Now this is the gassing valve, so also to now all air bubbles from the system, we get rid of all of them. Ensure doing getting rid of them, all valves are open to exclude all air from the system. Now we can close the valve and close the system and allow some air to come here to make the manometer ready. This length is fine. It's very important to have two levers are on the same lever before starting the experiment. If two levers are different, that means you have some pressure drop. You may have some air bubbles in the system. So now let's start the experiment. Okay. Now we'll do two experiments. We'll measure head loss in pipe. So we connected the manometer water to this pipe. Also, we connected, this is sudden contraction. So we connected this first point and second point to the mercury water system. Okay. So by this we can go measure both head loss continuously at the same water level. Now, when you open this, you will read this some readings, liter per minute. So this is the amount of water coming to the system. So let's start. Okay. Now, when the water increase, you will find that there is head loss. So the height here is different, and also the height over there is different as well. Okay, so there is different in height due to the friction, and here also different in the level due to the friction. So now let's increase again. As I increase the flow rate, you will find more friction in the system. So now the difference become higher, and here also the difference become higher. Okay, 1 and 2. So we'll take change the flow rate different times. Each time take the height of the manometers. You can, of course, you can put here to any parts you want to measure in the system. So this is all about experiment. One last thing I want to add: if you want to measure the pressure in valve, so you will connect between 2 points, but you have to increase to adjust until the opening, 50 opening, 30 opening, until the value you want, and then you can measure the pressure drop. So this is all about experiment. Thank you so much.